In this lecture, we'll discuss what trusses are and how they're used in the construction industry. We'll start with a few examples of trusses used in different structures. Trusses are often used as internal structures in roofs. Here you can see the installation of roof trusses. Trusses can also be used for the building envelope. This is the Mercantile Exchange Building in Chicago, often called the Chicago Merc. The black outer structure is a truss. This external truss is a distinctive structural feature designed to support the building's weight while allowing for open interior spaces. The exposed steel framework not only provides strength and stability, but also contributes to the building's industrial aesthetic. External trusses can be planar, as in the case of the Alcoa building in San Francisco. This building features an innovative external truss system that enhances the structural integrity while reducing the need for interior support columns. The design allows for greater flexibility in office layouts and highlights the building's modernist architectural approach. External trusses can also have complex shapes, like in the case of the Cocoon Tower in Tokyo. This Cocoon Tower is characterized by its striking diagonal truss structure, which not only provides seismic resistance, but also reinforces the tower's unique cocoon-like aesthetic. This exoskeleton framework enhances both the building's strength and its futuristic visual identity. The curved trusses are called space trusses. Here you can see another example of a space truss. The Swiss Re Tower in London, also known as the Gherkin. It features a distinctive external diagonal bracing system that enhances structural efficiency while minimizing the need for internal columns. This exoskeleton not only improves the building's wind resistance, but also contributes to its iconic curved silhouette. Trusses are also extensively used in road and railway bridges to support the deck. Trusses can be classified in three categories depending on the position of the deck relative to the truss. Here you can see a railway bridge with a deck supported by a steel truss. This truss is called a through truss because the deck goes through the truss and is connected to the bottom side of the truss. The Forth Railway Bridge in Scotland, built in 1890, features a massive cantilever truss structure designed to withstand strong winds and heavy rail traffic. Its interconnected triangular framework provides exceptional strength and stability, making it one of the most iconic and enduring engineering marvels of the 19th century. This is an example of a pony truss because the deck in this bridge passes in the middle of the truss. The Crumlin Viaduct featured a striking wrought iron truss structure which allowed to span the Ibu River valley with minimal material while maintaining strength. This truss is a deck truss because it supports the railway deck from underneath. Interestingly, the columns supporting this bridge were also made of trusses. Its lattice-like framework provided both stability and flexibility, making it one of the most impressive railway bridges of the 19th century before its demolition in 1966. Trusses also feature extensively in towers. Here are a few examples. The Tokyo Skytree features a lattice truss structure that provides exceptional earthquake resistance while maintaining a sleek, modern aesthetic. Its tapering framework distributes loads efficiently, allowing it to stand as the tallest structure in Japan. The Shukov Tower in Moscow is a pioneering hyperboloid truss structure designed by Vladimir Shukov, which minimizes material use while maximizing strength. Its open lattice design reduces wind resistance, making it both an engineering marvel and an architectural icon. And the famous Eiffel Tower is an iron truss masterpiece that uses a network of crisscrossing beams to distribute weight efficiently and withstand strong winds. Its structural ingenuity not only enabled its towering height at the time of construction, but also ensured its longevity as a global landmark. As we can see here, trusses in towers can be planar, as some trusses in the Eiffel Tower, or spatial, that is, following curved surfaces, such as in the case of the Tokyo Skytree and Shukov Towers. As you can see here, trusses are also used in pylons supporting electricity infrastructure. Cranes used in construction also consist of trusses. Here in this photo you can also see a dome which is supported by a space truss. This is Fuller's geodesic dome. It was built using a space truss made of 2 layers, one a triangular external grid and a hexagonal internal grid. Spatial trusses are also used in bridges. Here you can see the spiral bridge which was erected in Edinburgh at the old St James's Centre. This pony truss had a very complex shape following a curved pipe. And the European Space Agency and NASA also use trusses in space because of their structural efficiency and ease of construction. As we've seen, depending on complexity, trusses can be divided into planar and spatial. In this series of lectures, we will consider planar trusses. Trusses are widely used to support roofs. Here you can see a Fink roof truss. In this case, the roof load is transmitted to this truss through a series of purlins. Then, the truss transmits loads onto the columns or walls. Roof trusses have many different shapes. Here we can see a few examples. What is used in practice will depend on each project requirements, for example, roof space, low weight, and other constraints. Bridge trusses consist of 2 parallel trusses supporting a deck. The deck can be supported by the bottom or top belt of the truss. The load is transmitted by the truss from the deck to the abutments. Bridge trusses can also have many different shapes. The shape chosen for the project will depend on many factors included in each project's constraints. Trusses can be made of different materials, including metal, timber, combined from compressed timber members and tensile steel members, and concrete. In structural engineering, a truss is defined as a structure composed of slender members joined at their ends. In a truss, the members should be organised in such a way as to make the entire assembly behave as a single structural element. As we discussed in a previous lecture, cables can carry only tension. This is different from truss elements that can carry tension and compression. The tension members are called ties, while the compression members are called struts. To distinguish between tension and compression, tension forces are treated as positive, while compression forces are treated as negative. Modelling the connection between members in a truss is important for developing methods for truss analysis. It is assumed that the members in a truss are connected by pin joints or hinges. Pin joint rotations do not prevent rotation. Loads in a truss are applied at the joints only. A typical pin joint is shown here. As you can see, this connection prevents movement but allows for rotation. Truss members can be divided into the top and bottom chords, also called belts. The chords are connected by verticals and diagonals. Trusses are made of cells. Let's consider how truss cells are built. Pin joints and truss members can be combined in a cell in different ways. A cell can have 3, 4, 5 or more members. For a truss to be stable, every truss cell should be stable. Out of the cells shown in this slide, only the triangular cell is stable. Other cells can change their shape. As we saw, the triangle is the simplest stable truss cell. Therefore, the truss stays stable if it is built only from triangular cells. Construction of a stable truss starts from a triangular cell by adding members and nodes. To create a new stable cell in a truss, 1 node and 2 members are required. Let's build a stable truss from triangular cells. We start with 1 truss cell, which consists of 3 hinges and 3 members. By adding 2 stable cells, the truss grows to 5 nodes and 7 members. Adding another 2 stable cells, the truss can grow to 7 nodes and 11 members. Then the truss will grow to 9 nodes and 15 members, and so on, and so on, and so on. As a result, we can define a relation between the number of joints and members. In the analysis, truss joints are assumed pinned. In real trusses, however, the joints can be pinned or fixed. The pin joints are usually introduced at supports using bolted connections, while the trusses are usually built with fixed joints using bolted, riveted or welded gusset plates. Trusses with fixed joints are still analysed as having pin joints. Let's discuss how a real truss is modelled. Here you can see a timber truss with a top joint being made of a bolted gusset plate, while the bottom joint is made of a bolted connection. During the translation of this truss into the analysis space, the members in the truss are substituted by bars and the joints by hinges. The real truss is then discarded and the obtained model is analysed. Let's look at a few basic types of trusses. This is a Pratt truss. In this truss, the diagonals are directed towards the middle and downwards. This is a Howe truss. In this truss, the diagonals are directed to the middle and upwards. In a Warren truss, both types of diagonals are present. This is a Fink truss. Since this truss is used in roofs, its top belt is inclined. And this is a Bollman truss. As you can see here, this truss has a large number of diagonals which can connect different cells. Trusses are very popular in the construction industry due to several advantages. They are very efficient structurally since they have a relatively high strength and low weight. Because their members work mainly in compression and tension, the trusses are very stiff and have low deflection. As a result, trusses are often used for covering long spans. Additionally, trusses are composed from small members and can be easily fabricated on a building site. Thank you for joining me for this introduction into trusses. I hope you'll join me to discover how we can actually analyse trusses using the method of joints and the method of sections, and to solve some trusses together. Bye for now.